School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 3 Sampling and Sampling Distributions. Unit 9 Sampling Methods. Part 1.
After completing this unit, you should be able to appreciate why sampling is so common in managerial situations, identify the potential sampling errors, list the various sampling methods with their strengths and weaknesses, distinguish between probability and non-probability sampling, know when to use the proportional or the disproportional stratified sampling, understand the role of multi-stage and multi-phase sampling in large sampling studies, appreciate why and how non-probability sampling is used in spite of its theoretical weaknesses, and recognize the factors which affect the sample size decision. Introduction. Let us analyze the 5 situations to find out the common features among them, if any. Number 1. An inspector from the Weights and Measures Department of the government goes to a unit manufacturing Vanaspati. He picks up a small number of packed containers from the day's production, pours out the contents from each of these selected containers, and weighs them individually to determine if the manufacturing unit is packing enough Vanaspati in its containers to conform to what is claimed as the net weight in the label. Number 2. The personnel department of a large bank wants to measure the level of employee motivation and morale so that it can initiate appropriate measures to help improve the same. It administers a questionnaire to about 250 employees from different branches and offices all over India, selected from a total of about 30,000 employees, and analyze the information contained in these 250 filled-in questionnaires to assess the morale and motivation levels of all employees. Number 3. The product development department of a consumer products company has developed a new improved version of its talcum powder. Before launching the new product, the marketing department gives a container of the old version first, and after a week, a container of the new version to a group of 400 consumers and gets the feedback of these consumers on various attributes of the products. These consumer responses will form the basis for assessing the consumer perception of the new talcum powder as compared to the old talcum powder. Number 4. The quality control department of a company manufacturing fluorescent tubes checks the life of its products by picking up 15 of its tubes at random and letting them burn till each one of them fuses. The life of all its products is assessed based on the performance of these 15 tubes. Number 5. An industrial engineer takes 100 rounds of the shop floor over a period of 6 days, and based on these 100 observations, assesses the machine utilization on the shop floor. What is sampling? On the face of it, there is little that is common among the 5 situations described so far. Each one refers to a different functional area, and the nature of the problem also is quite different from one situation to another. However, on closer observation, it appears that in all these situations, one is interested in measuring some attribute of a large or infinite group of elements by studying only a part of that group. This process of inferring something about a large group of elements by studying only a part of it is referred to as sampling. Most of us use sampling in our daily life. For example, when we go to buy provisions from a grocery, we might sample a few grains of rice or wheat to infer the quality of a whole bag of it. In this unit, we shall study why sampling works and the various methods of sampling available so that we can make the process of sampling more efficient. Some basic concepts. We shall refer to the collection of all elements about which some inference is to be made as the population. For example, in the second situation, the population is the set of 30,000 employees working in the bank. And in the third situation, the population comprises of all the consumers of talcum powder in the country. We are basically interested in measuring some characteristics of the population. This could be the average life of a fluorescent tube, the percentage of consumers of talcum powder who preferred the new improved talcum powder to the old one, or the percentage of time a machine is being used, as in situation number 5. Any characteristic of a population will be referred to as a parameter of the population. In sampling, some population parameter is inferred by studying only a part of the population. We shall refer to the part of the population that has been chosen as a sample. Sampling therefore refers to the process of choosing a sample from the population so that some inference about the population can be made by studying the sample. For example, the sample in situation number 2 consists of the 250 employees from different branches and offices of the bank. Any characteristic of a sample is called a statistic. For example, the mean life of the sample of 15 tubes in situation number 4 is a sample statistic. Conventionally, population parameters are denoted by Greek or capital letters and sample statistics by lowercase Roman letters. There can be exceptions to this form of notation. For example, population proportions is usually denoted by capital P and the sample proportion by small p. Sampling is not the only process available for making inferences about a population. For small populations, it may be feasible and practical and sometimes desirable to examine every member of the population. For example, for inspection of some aircraft components. This process is referred to as census or complete enumeration of the population. Here are the various reasons which make sampling a desirable and in many cases the only course open for making an inference about a population. Number 1. Time taken for the study. Inferring from a sample can be much faster than from a complete enumeration of the population because fewer elements are being studied. In the third situation of the previous section, a complete enumeration of all consumers, even if feasible, would perhaps take so much time that it is unacceptable for product launch decisions. Number 2. Cost involved for the study. Sampling also helps in substantial cost reductions as compared to census, and a better sample design could reduce the cost of the study further. In many cases, like in the second situation of the previous section, it may be too costly, although feasible, to contact all the employees in the bank and get information from them. Number 3. Physical impossibility of complete enumeration. In many situations, the element being studied gets destroyed while being tested. The fluorescent tubes in the situation number 4, which are chosen for testing their lives, get destroyed while being tested. In such cases, a complete enumeration is impossible as there would be no population left after such an enumeration. Number 4. Practical infeasibility of complete enumeration. Quite often, it is practically infeasible to do a complete enumeration due to many practical difficulties. For example, in situation number 3, it would be infeasible to collect information from all the consumers of talcum powder in India. Some consumers would have moved from one place to another during the period of study. Some others would have stopped consuming talcum powder just before the period of study, whereas some others would have been users of talcum powder during the period of study, but would have stopped using it sometime later. In such situations, although it is theoretically possible to do a complete enumeration, it is practically infeasible to do that. Number 5. Enough reliability of inference based on sampling. In many cases, sampling provides adequate information so that not much additional reliability can be gained with complete enumeration in spite of spending large amounts of additional money and time. It is also possible to quantify the magnitude of possible error on using some types of sampling. Number 6. Quality of data collected. For large populations, complete enumeration also suffers from the possibility of spurious or unreliable data collected by the enumerators. On the other hand, there is greater confidence on the purity of the data collected in sampling, as there can be better interviewing, better training and supervision of enumerators, better analysis of missing data, and so on. Types of sampling. There are two basic types of sampling depending on who or what is allowed to govern the selection of the sample. We shall call them by the names of probability sampling and non-probability sampling. Probability sampling. In probability sampling, the decision whether a particular element is included in the sample or not is governed by chance alone. All probability sampling designs ensure that each element in the population has some non-zero probability of getting included in the sample. This would mean defining a procedure for picking up the sample based on chance and avoiding changes in the sample except by way of a predefined process again. The picking up of the sample is therefore totally insulated against the judgment, convenience, or whims of any person involved with the study. That is why probability sampling procedures tend to become rigorous and at times quite time-consuming to ensure that each element has a non-zero probability of getting included in the sample. On the other hand, when probability sampling designs are used, it is possible to quantify the magnitude of the likely error in the inference made, and this is of great help in many situations in building up confidence in the inference. Non-probability sampling. Any sampling process which does not ensure some non-zero probability for each element in the population to be included in the sample would belong to the category of non-probability sampling. In this case, samples may be picked up based on the judgment or convenience of the enumerator. Usually, the complete sample is not decided at the beginning of the study, but it evolves as the study progresses. However, the very same factors which govern the selection of a sample, for example, judgment or convenience, can also introduce biases in the study. Moreover, there is no way that the magnitude of errors can be quantified where non-probability sampling designs are used. Many times, samples are selected by interviewers or enumerators at random, meaning that the actual sample selection is left to the discretion of the enumerators. Such a sampling design would also belong to the non-probability sampling category and not the category of probability or random sampling. Probability sampling methods. In the category of probability sampling, we shall discuss 4 designs. Number 1, simple random sampling. Number 2, systematic sampling. Number 3, stratified sampling. And number 4, cluster sampling. One can also use sampling designs which are combinations of all these 4. Simple random sampling. Conceptually, simple random sampling is one of the simplest sampling designs and can work well for relatively small populations. However, there are many practical problems when one tries to use simple random sampling for large populations. What is simple random sampling? Suppose we have a population having n elements and that we want to pick up a sample of size n, that is, which is less than capital N. Obviously, there are many possible samples of size n, that is, small n. Simple random sampling is a process which ensures that each of the samples of size n has an equal probability of being picked up as the chosen sample. This also implies that under simple random sampling, each element of the population has an equal probability of getting included in the sample. All other forms of probability sampling use this basic concept of simple random sampling but apply to a part of the population at a time and not to the whole population. Sampling with and without replacement. We have implicitly assumed that we are sampling without replacement, that is, if an element is picked up once, it is not available to be picked up again. This is how most practical samples are. But as a concept, it is possible to think in terms of sampling with replacement, in which case an element after being picked up and included in the sample is replaced in the population so that it can be picked up again. What is important for us to note at this stage is that even in the case of simple random sampling with replacement, each element has an equal probability of getting included in the sample. How is simple random sampling done? It is imperative to have a list of all the members of the population before a simple random sample can be picked up. Such an exhaustive list of all population members is called a sampling frame. Suppose we write the name of one such member on a chit of paper and thus have capital N chits in a bowl, one chit for each member of the population. We can then mix the chits well and pick up one chit at random to represent one member of the sample. If we want a sample of size small n, we have to repeat this process small n times and we shall have a simple random sample of size small n consisting of the names of members appearing on the chits picked. It is easy to observe that if we replace the chits in the bowl after noting down the name of the element, we will have a simple random sample with replacement and one without replacement if we do not replace the chits. As the population size increases, it becomes more and more difficult to work with chits, and one can simulate this process on a computer or by using a table of random numbers. We can associate a serial number with each member of our population and then instruct a computer to pick up a member from 1 through capital N using its pseudo-random number generator. This ensures that every number from 1 through capital N has an equal probability of getting picked up, and so the sample selected is a simple random sample. We can also use a table of random numbers to pick up a simple random sample. In a table of random numbers, there is an equal probability for any digit from 0 to 9 to appear in any particular position. The most important thing in using a random number table is to specify to the minutest detail of the sequence of steps that has been decided before the table is actually referred to. Suppose we have a population of size 900 with each number being given a serial number ranging from 000 through 899 and we want to pick up a simple random sample of size 20. We proceed by defining a procedure. Number 1. Starting point and direction of movement. We may decide to start with the top left hand number and consider the first 3 digits from left as the 3-digited random number picked up. For example, the first number would then be 121. We also specify that we shall move down a column to pick up further numbers. For example, the second number would be 073. If there is no further number down the column, we shall go to the top of the next column of 5-digited numbers and pick up the first 3 digits from left. For example, after 851, our next number shall be 651. Number 2. Checking the number picked up. If the number picked up is in the range 000 to 899, we accept the number, but if it is outside this range, we shall discard it and pick up the next number. For example, after the third number 703, we discard 934 and the fourth number of the sample would be 740. Similarly, if we are doing sampling without replacement and a number is picked up again, it is discarded and we move to the next 3-digited number. Using this process, if we want a sample size of 10, our sample would contain members with the numbers like 121, 073, 703, 740, 736, 513, 464, 571, 379 and 412. Simple random sampling in practice. Simple random sampling as described here is not the most efficient sampling design either statistically or economically in all practical situations. However, it forms the basis for all other forms of probability sampling which are used on parts of the population or subpopulation and not on the population as a whole. As mentioned earlier, in listing all members of the population with a frame is required before a simple random sample can be chosen. In many situations, the frame is not available nor is it practical to prepare the frame in a time and cost-effective manner. Obviously, under such conditions, simple random sampling is not a viable sampling design. Most large populations are not homogeneous and can be broken down into more homogeneous units. In such conditions, one can design sampling schemes which are statistically more efficient, meaning that they allow the same precision from smaller sample sizes. Similarly, by picking up members from geographically closer areas, the cost efficiency of the sampling design can be improved. Cluster sampling is based on this concept. The process of picking up a simple random sample through using a table of random numbers or any other such aids as discussed earlier is rather cumbersome and not very purposeful to the uninitiated interviewer. Simpler forms of sampling overcomes this handicap of simple random sampling. Systematic sampling. Systematic sampling proceeds by picking up one element after a fixed interval depending on the sampling ratio. For example, if we want to have a sample of size 10 from a population of size 100, our sampling ratio would be small n over capital N, which is equal to 10 over 100, which is equal to 1 by 10. We would therefore have to decide where to start from among the first 10 names in our frame. If this number happens to be 7, for example, then the sample would contain members having serial numbers 7, 17, 27 and so on till 97 in the frame. It is to be noted that the random process establishes only the first member of the sample. The rest are preordained automatic because of the known sampling ratio. Systematic sampling in the previous example would choose 1 out of 10 possible samples, each starting with either number 1 or number 2 or number 10. This is usually decided by allowing chance to play its role. For example, by using a table of random numbers. Systematic sampling is relatively much easier to implement compared to simple random sampling. However, there is one possibility that should be guarded against while using systematic sampling, that is the possibility of a strong bias in the results if there is any periodicity in the frame that parallels the sampling ratio. One can give some ridiculously simple example to highlight the point. If you were making studies on the demand for various banking transactions in a bank branch by studying the demand on some days randomly selected by systematic sampling, be sure that your sampling ratio is not 1 by 7 or 1 by 14, etc. Otherwise, you would always be studying the demand on the same day of the week and your inferences could be biased depending on whether the day selected is a Monday or a Friday and so on. Similarly, when the frame contains addresses of flats and buildings all alike and having say 12 flats in one building, systematic sampling with a sampling ratio of 1 by 6, 1 by 60 or any other such fraction would bias your sample with flats of only one type. For example, a ground floor corner flat, that is, all types of flats would not be members of your sample and this might lead to bias in the inference made. If the frame is arranged in an order ascending or descending of some attribute, then the location of the first sample element may affect the result of the study. For example, if our frame contains a list of students arranged in a descending order of their percentage in the previous examination and we are picking a systematic sample with a sampling ratio of 1 by 50, and if the first number picked is 1 or 2, then the sample chosen will be academically much better off compared to another systematic sample with the first number chosen as 49 or 50. In such situations, One should devise ways of nullifying the effect of bias due to starting number by insisting on multiple starts after a small cycle or other such means. On the other hand, if the frame is so arranged that similar elements are grouped together, then systematic sampling produces almost a proportional stratified sample and would be therefore more statistically efficient than simple random sampling. Systematic sampling is perhaps the most commonly used method among the probability sampling designs and for many purposes. For example, for estimating the precision of the results, systematic samples are treated as simple random samples.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Voiceover by Harpreet Kaur. Edited by Savita. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.